Hello everybody, hope you guys are doing well. So continuing on our journey, today we will be learning more about how what relational algebra is, and we'll see a little bit more about them, and then we'll go on from there. So basically today we are going to learn about relational algebra, and then we'll see how does how do the query work, and then we'll go on from there. So here we'll be basically studying two formal query languages associated with the relational model. Now, query languages are specialized languages for asking questions or queries that involve the data in the database. After covering some preliminaries, we will see the relational algebra that are composed using a collection of operators. Now, each query describes a step-by-step process. So basically, okay, now we begin by clarifying some important points about relational queries. The inputs and outputs of a query. Okay, so basically, there are a few points that we need to be that we need to take care of. First is basically input to a query is going to be a relational is a relation, and the output of a query is also going to be a relation. Now, due to these considerations, now we use now query is evaluated using instances of each input relation produces an instance of output relation. Now we will see we used field names to refer, right? Okay. Now in defining a relational algebra and calculus, the alternative of referring of fields by position is more convenient than referring to fields by positions. Queries often involve computation of intermediate results, which are themselves relational language constructs. So we'll see later on. We present a sample of using the following schema. So to come back, so this is the schema, right? Our schema is the table. To quickly read this is going to be my schema. The schema is my table. So I had two things, right? Relational instances in that. So in this I'll be so these are basically, so these individual tuples are what we call as uh these are tuples present, right? So these tuples are uh these are called as relations. Now if you break further down, so we have different columns, right? So you have column 1, you have column 2, so yeah, there are different columns, so you can say we have different columns here. uh so these are called as attributes or fields, right? So these are nothing but my fields, or you can call them as attributes. Now let's go further, right? Now let's start with relations projection. Now the relational algebra is one of the two formal query languages associated with the relational model. So this is the relational model, right? This is nothing but called as our relational model. And then you have something called as domain name. Domain name basically indicates what type of value each column is going to take. So relational algebra is one of the two formal query languages associated with the relational model. Queries in algebra are composed using a collection of operations. A fundamental operator property is that every operator in the algebra will accept one or two relational instances as arguments and retain a relational instance as a result. The property makes it easier to compose operators to form a complex query. A relational algebra expression is recursively okay. We describe the basic operators as So you have basic operators, selection, projection, union, cross product, difference, as well as some additional operators that can be defined in terms of basic operators, but that arise frequently enough to warrant special attention. Now in the following sections, now each relation query describes the step-by-step procedure for computing the desired answer. So right now our job is only basically to query, right? So we need that so we said relational model has two things, right? One is the relational calculus. So I can say this is comprised of two things. You have relational calculus and then you have relational algebra, right? You have relational calculus and you have relational. Now the job of relational algebra is basically this is how internally the queries are written, right? Like internally how the queries will be working. Basically this is to compute and give us the desired uh, compute and give us the desired row or relation, right? Now the formal way of writing is nothing but relational calculus. So this is basically how we write. So this is formal writing. So now there are certain operators, right? Fundamental operators in relational algebra. We'll see one of them. So first is basically selection and projection. Now relational algebra includes operators to select rows from a relation and to project columns. Now these operations allow us to manipulate data in a single relation. The first thing that we are going to learn is basically selection and projection. Okay. Now we can retrieve rows. The selection is basically given by the sigma and project columns projection is given by pi. So this is how it is denoted in relational calculus. Now what the sigma does is, now this is basically used to select a row. So you are going to select a specific row and give it as the output. Now pi is to project columns. Now projection we can retrieve rows corresponding to expert by using the sigma operator. Uh, Now the selection operator specifies the tuples to retain through a selection condition. In general, okay, so with this select operator, what we would be doing is we would be specifying a condition. Okay. Now what is projection? Okay, now the projection operator allows us to extract columns from a relation. So basically this is, oh, this is for selecting a row, this is for giving a specific column. So this is like column. Now whenever you are using selection, right, with this we would be specifying some extra constraints or some extra conditions. Basically that will be logical connections, right? So basically, for example, it could be a comparison operator that we can use. So we can say comparison operator. uh, for example, the most commonly used comparison operator that we have is basically less than, greater than, equal to, less than, equal to, not equal to, and then or greater than, so yeah, greater than. So this is basically comparisons, right? The reference to an attribute can be by position or by name. So either you can do it by like uh, So okay, for example, this is, let's consider a table itself. So that, so I have this table here. So you have different columns here. You have SID, name, rating, and age. So this is 28. Now name is repeat, rating is 9, age is then again you have some student ID. This is, you can write anything, or this is just an example, right? So I suppose I want to select this specific row, right? So what he's trying to say is there is two ways to select. Now either you can do using uh so these are attributes, right? Okay, so this is attributes. So these attributes will be either referenced by position. So like one is by position or other is by dot. For example, using dot and then the attribute name. So for example, this is this attribute name, right? So for I to select a row in which the rating attribute is greater than 9, so then I would be selecting this row, right? Because this has a row that is greater than 9. So this is going to give me a relation, right? Remember. Okay, for example, so yeah, basic. So this is what I'm going to get when it's going to produce me a row. So the final output will be a row, right? So the output will be uh this is 58, this is Rushdie, this is 10, and then this is that number. So this is how the final output is going to look, right? The next thing that we have is basically something called as selection, right? So now this is the selection. Now we are going to do projection, basically selecting a column, specific column. So for example, okay, so this is the table, right? Let's shrink it down. Yeah, suppose this is table, and this table has two rows. And this is S name, and then this is So now, uh, so basically, so now what I'm going to do is I'm going to do a projection. So I'm going to say projection and say give me as name. So when I do this, uh, the final output that I'm going to have is basically the S name. So this is the S name column, and then you have this is your pay and copy. So this is basically selecting the column, right? So now this is the projection of column S name. So we're going to make now. So uh now the projection operator allows us to extract column from a relation. For example, we can find out all sailors' names. Okay, this is evaluates. The subscript rating specifies how the fields to be retained. Okay. Now, suppose that we want to find out only the age of sailor, so then we can do something as some conditional. Okay, now since the result of a relational algebra expression is always a relation, we can substitute an expression wherever a relation is expected. For example, we can compute the name. So what is doing? Okay, now since the result of a relational algebra expression is always a relation, we can substitute an expression where a relation is expected. For example, we can compute the name and ratings. What he's trying to say is you can combine projection. Okay, now this suppose that we want to find out the expression evaluates although three sailors a single tuple appear the result of this projection what is trying to say the result of a relational expression is always a relation. We can substitute an expression wherever a relation is expected. What is this? What is he trying to say exactly? Every operation in relational algebra or join will produce a relation as its result. Because of that, you can nest relational algebra. Oh, so what is okay? So, uh, now this is but projection. Also, what you're trying to say is even though projection, it appears that we are returning a column here. Although we are saying that a column is going to come, but even though the projection selects the output is still a relation, right? But then yeah, so this still can be considered a relation. But it's a relation, but then it's a relation but less columns. It's a relation with less columns. Output is always going to be a row. So what he's saying is he's saying whatever you use in relational algebra will always give you a column. So this is always the result. Right. The result will always be a relation. But then you may say, how is this working in projection? The only difference in projection is uh, in projection it is a uh, relation with less columns. Now, since all the answer, like all of them will eventually give us a relation, right? Since eventually we are going to result to a relation, we can nest them, or you can say nesting can be done here because eventually the result is going to be a relation, so then nesting can be done. Okay, now then you have something called as set operations, right? Now there are standard set operations that we are going to see. Okay, so the next thing that we have in relational set operations. And these are standard set operations. So the first we have is basically union. Now union returns a relation containing all tuples that occur in a relation instance or a relation instance or both. For example, the two relation instances are said to be non-compatible with the following. They have the same number of fields, corresponding fields taken out from left to right, and other. Now union, it returns a relation, so it is going to eventually return a relation. Okay, that is understood because, and then uh, either relations or relation or both. Now two are said to be union compatible if the following. Now what is this? There is some conditions for union compatibility. What is this? Let's see. Oh no. Uh, since there is okay. Now combines. There is something called as where it says human compatible. Oh, so now when I'm doing union between two, when I'm trying to do a union between two relations. So when does union happen? First is same number of attributes. So attributes are nothing but my column, right? Or columns. The second condition is that they have the same domain. So domain is same. Okay. Now is intersection or returns a relation instance containing all tuples that occur both R and S. Now the relation must be so okay. Now yeah, deduction is basically now the second operation that we have is intersection, right? Again, they should be union compatible. So if I want to do intersection, first condition is union compatibility has to be there. Then what else is saying is intersection uh, and the schema. Okay, basically what is this going to return is common relations. Then I have set difference. Now returns and relationship containing all tuples that are in R but not in. Okay, now difference is again, this is like union minus intersection. Difference is in one, not in other. So you can understand this in using Venn diagram much better. The cross product returns the relation whose schema contains all the fields on the same followed. Oh, now this is something. Now what is cross product? So when we are going to do cross product, what is going to happen is uh, the fields of are in the same order followed by okay. So if I'm doing a cross product, then the resultant will be fields of R followed by the other one fields, right? So for example, let's take an example of cross product. If a cross product is let's do a cross product. So I am doing a cross product of which two. It's if it's a cross product. Uh, but it is between which two? Mm, well, let's see. Cross product is something that we need to see. Okay, so first is basically I have two relations. Okay, let's see example of all the set one by one. So first is going to be my union. So first is union. So I have two tables, right? Okay, table one, and then I have columns, right? So this is having exactly two. This is 1, 2. So now when I do a union, what is going to happen is, so I'm going to have all of them, right? But then now first is I'm going to check whether they're having, is it union compatible? Yeah, I have same number of columns, and domain name also is same, right? Column and domain both are working. So now when I do union, it combines all tuples from both R and S. But then if there is something which is common, it does not repeat, I guess. So the output will be, because this so this is present in both, right? So it's not going to repeat this one. It's only going to put it once. So my final will be, I'll have two columns here, and then I'll have three tuples. It's going to be one Alice, two Bob. Okay, I need to have. And then the third one is basically three, and then here is. So basically, this is how it is going to be represented, right? So this is my union. The thing is, this is only going to come once. The reason behind this is there is no repetition, right? And now the second example is intersection. Intersection between these two is going to be, so this is the common thing, right? So intersection will have only one. Okay. So intersection will have one tuple which is common. So the two one is common, right? So let's have the two thing here. This is two, and I guess that was Bob. Yeah. The next thing that I'm going to have is difference, right? So when I do difference, uh, so common minus, so Alice and Charlie should be the answer, I guess. So return the tuples that is in our, okay. So when I do difference, it returns the tuple of the first one, not the both of them. So if this is say difference, only returns only returns tuple from uh, this one, which are not which are not in S, not in this. So if I do a subtraction, then the answer will be, let's see, let's go back. So what is, this is common, right? So this won't come as it's present in here as well. So final will be only this one LS. Now a cross product. Now this is something cool. It returns all possible combinations of R and S. So all possible combinations. If I have, this is a 2 cross 2, right? So I have 2 rows. So if I do all possible combinations, it is going to be cross. It is going to be 4. 4. Okay. So cross product, it's like multiplying all possible combinations. And this is the first step to our join, or it's called as first step towards join. So now if I do on all possible of these two, it will be, so 2 cross 2, right? You can have any one of them, both. Either you can have front. So first is going to, first I need 4. So my first thing is I need 4 columns here, because all possible, right? This is row. So all possible. Again, these need to be union compatible. So these are all compatible, right? So I have 1, 2, 3, 4. So it will be, so first row with first of the other, first row with second of the other. You can, anyhow you can get. So it will, oh, it will be, oh, we need one more here. Oh, this one, oh, this one. Let's just write it. Say. So this is Bob. So in all we have 4 possible combinations, right? So we have 1, 2, 3, 4. So these are all 4 possible combinations. Now this is the first step towards a join, right? Now we are not matching anything, we are just giving all possible combinations, right? Nothing is going to happen here. Now the only caveat is here we do not need to be union compatible. So union compatibility is not, we don't need it over here, because we are just doing one with the other, right? So if it is also not union compatible, then it will still work. Okay. Now the next thing that we have is basically join, right? The join operator is one of the most widely used in relational algebra, most common way to combine information from 2 or more relations. Although a join can be defined as a cross product followed by a selection and projection, join arise much more frequently in practice than their plain cross product. Further, the result of a cross product is typically much larger than the result of a join. It's very important to recognize joins and implementation without materializing the underlying cross product by applying the selection and projection on the fly. For same reason, joins have received a lot of attention. There are several variants. So now what is trying to say? This is one of the most important relational algebra that we will be using. So joins. Again, this is very important. One of the most important feature that we would be using here. Now, joins can be said as cross product. It is a cross product, and then by selection. So selection can be, we can do two, right? We can do projection and selection. The join is nothing but first you do a cross product and then you apply a selection. The more general version of the join accepts a join conditions and a pair of relations. So for example, this is again The first thing we will compute the cross product, and then we will do selection based on the okay. So first is the first type of join that we have here is, you can have different types of joins. So joins can be of different types. So first is uh, conditional. So conditional will be uh, cross product and then a selection criteria. So cross product plus selection criteria. Now common special case of the join operation. So when we are only when this selection criteria only deals with equal, we call them as equijoins. Okay. Now natural join is further a special case of the join in which equalities are specified on all fields having the same. So basically then we have something called as natural join. So natural join is uh, on equality on all fields. So first is a theta join. A theta join is based on a condition. The equijoin is condition is equal. Natural join automatically joins relations all attributes with the same name. Let's let's go with an example of each. Uh, Now what does SQL do is, so basically SQL is based on uh, now why are we learning this algebra? So what happens is, internally what the management system is going to do is, so for example you have written a query. So this is select name, where age is greater than 18. So first DBMS parses the syntax. This is SQL like syntax, right? So then I'm going to generate that logic tree. From there I'm going to interpret it as a relational calculus, then convert it into relational algebra. So after I have relational, then I do a relational algebra conversion, and then I execute. So this logic tree is nothing but my relational calculus. So let's see, let's understand with an example. So now first, so this is I have written. I am going to write this, right. Select. Say I have a table name. Say I have a table student that has a attribute name. Then I am going to do where age is greater than 18. The way this is going to work is, Now DBMS is first going to convert it to something called as a tuple relational calculus, right? So it's going to say tuple dot name, and where tuple belongs to student, and then I'm going to have an condition t dot age greater than 10. So t is the tuple variable. We declare the condition. So this is the condition, right? This one is the condition. Now relational algebra, how to compute it is the actual. So now this is now going to get convert. So I'm going to do a projection, right? I'm going to do a select. So we need to select rows which are having age greater than 18, right? So this is for column, right? I'm going to select name column, but when my row is this, right? So first I'm going to do sigma of age greater than 18, and then which table. Once I have this, and then I'm going to project this name, right? I need only projection of name. This is the relational algebra, how it's going to be. This is what is going to work down the down the so this is then the physical extension is the DBS might use an index or an age if available, apply a filter and only extract only the name as a result. So this is how it's going to work internally, right? So the thing is, if I'm saying uh, if my cross product is the beginning of join, so I say for each join in theory it is going to calculate the cross product. You have any join. Now we haven't, so theoretically for each and every possible join that we write, we are going to do a cross product, right? But then uh, if you think it that way, then if it's a very big table, right, so then it is not going to be optimized in that. So then we will do some sort of optimization process that is inherently there in the database itself, right? So if I say SQL is nothing but math, the only difference is that what do you say, the only caveat is um, the input is the input instead of giving numbers. So SQL is basically a mathematical operation, can we say it, where the input and output both are relations. Yeah, so basically SQL is just one mathematical foundation, that is relational algebra and calculus, where both is an input, another is an output. Now how are we going to okay, so here we have the scope of optimization, right? Because now we know how it's internally each and every query is going to work. So whenever you're doing join, it is a very heavy operation to be performed, because internally we are going to do a cross product. The low level is basically a mathematical cross product. So SQL is math. It's a practical implementation of relational algebra and calculus. But how did we come across this? So Edgar F. Cod was a British computer scientist who basically developed. Oh, so this all is so what he did is, oh, so if you go back, the way EF Cod or the way Edgar F. Cod produced it, he said that this is math. He treated this as a sets of tables. So he treated, and when he performed those operations, then he said, uh, so Cod realized that tables are relations and rows are tuples. So basically, he used logical ways to implement. Now it's very difficult for a common man to or for a programmer to write these mathematics, right? So we wanted some abstraction so that uh, we could write it in a normal English language, which is much more easily understandable. So then he found a way to link math to queries. Uh, so what he did is basically he converted those uh, chord breakthrough was converting a mathematical logical structure that could understand human understandable queries, right? So he didn't stop at theory because he just proposed the like he did. So underlying it's all math. So underlying DF code used math, but what he did is he kind of built this relation of math with an English understandable or a human understandable form, which is the query language that we use. Okay, so I guess yeah, that is all for this session. I hope you guys liked it. I'll see you guys in the next one. Till that time, take care, bye bye, and please subscribe to my channel. Yeah, bye.